Right, good morning. You should all have your homework, and the solution to the homework I just sent out over Moodle this morning, so it's either you ought to have gotten an email of the solutions attached or you soon will be. I want to say a few things about the homework assignment. First of all, as we mentioned before, significant figures. I'm not grading on significant figures, but oftentimes I notice in the homework I get sort of a ridiculous number of significant figures. Just try to be reasonable on that. I'll probably continue putting little notes, but I won't be taking off points. Units is a similar situation. I won't be taking off units except in a few cases. If the units are unclear, it's not obvious what the units are. For instance, I ask you to estimate the size of something and you write down 6. And I don't know if that's microns or nanometers or what. I mean, then the units become really crucial and you might lose some points. But in general, if the units are obvious, you're calculating some forces and you don't put newtons after one of the forces, but it's obvious they're all in newtons, I'm not going to usually take off, but I may note it. You will probably lose more credit if your answer is way off than if it's close, even if it's a similar type of just a numerical error. And that's because I want you to think about your answer. And to just give you one example, in one of the first problems where you had to estimate the size of the nucleus based on the volume of DNA in your body, if you came up with an answer that was on the order of, say, a third of a meter or a meter, well, think about it. Every cell in our body has that nucleus in there. If the nucleus was the size of a third of a meter, it's just not going to make sense. So I want you to think about your answers and make sure that they make at least reasonable sense. Another issue is sometimes in calculations where, for instance, suppose you were calculating a height using hydrostatic equations, and that would become from the pressure over rho times G. Well, now if you're going to use MKS units or SI units, you're going to need to express the pressure in pascals. We have a bunch of units for pressure, and if you express it in millimeters mercury or atmospheres or something, you're going to get funny units for H. So you need to express, in most equations, you need to use SI units. Occasionally all the units will cancel out, like in the equation where we set sum of the torques equal to 0, you'll get lucky and you can put it in any units you want for the length. But in general, you want to use SI units when you're using an equation. The derivation is important. A lot of people have trouble with the Murray's Law derivation, but quite a few of you went through and made a derivation. You got the right answer, but the derivation was 4/3 pi r parent cubed equals 4/3 pi r d1 cubed plus 4/3 pi r d2 cubed. Okay, well, cancel out the 4/3 pi's and you get Murray's Law. The cube of the parent is the sum of the cubes of the daughters. But 4/3 pi r cubed, that's the volume of a sphere. We're dealing with cylinders, and we wanted you to use the fact that the shear force was the same in each of them. In this case, the derivation just didn't make any sense. It was a coincidence that you got it right. So I did take off points if you don't get the derivation right. And that means that if you just wrote down the answer, you're also going to lose some points. I want to see some work to see how you got your answer. So keep that in mind as we go forward. Finally, problem 1.16 was the problem of standing on your head. And most of you gave me the answer that I mentioned in class, which was correct. It's the same answer that's in the answer key. But as I was grading it, I got to thinking, really, why are we so uncomfortable when we stand on our head? And I have a feeling it might be related not only to our blood vessels under high pressure, but we have sinuses, air pockets in our head. And I wouldn't be surprised if what actually we're feeling is uncomfort because those sinuses are getting compressed more than and causing air pressure difference between the sinuses and the outer ear. Those kind of things might be what we're feeling more than I think the blood pressure issue is still real, but it may not be what makes us uncomfortable in the short term. Anyways, food for thought, but sometimes I learn things when I'm grading your guys' assignments, as well as hopefully you guys learning things. Okay, any questions about the homework in general, not about specific problems. Maybe you can talk to me after class, but in general, how it goes, what's happening. Okay, you'll have another assignment which is due this Friday. It'll be over Chapter 2, and we're going to finish Chapter 2 today. So we'll talk about some of the other homework problems today, and then you should be able to get rolling on that. All right. In that case, I want to start talking a little more about animal scaling. We talked about this last class with that example of an animal falling through a viscous medium. Now today we're going to be going pretty soon to Chapter 3, starting on Wednesday. Chapter 3 is thermodynamics. So I want to bring in some of those ideas here at the end of Chapter 2, and I want to ask, how do animals stay cool? Okay? And that's an interesting question, because we have to compare heat production versus heat loss on a typical animal. And in almost all of these arguments about scaling, we're going to consider animals that are the same shape but different sizes. So if you want to think of them as spheres, they're just spheres of different radii, or maybe you think of a more realistic shape, but it's going to be a shape that scales up and down. First of all, let's think about how your animal produces heat. Okay, it's got a metabolism. And metabolism means it's going to be producing heat, and we're going to introduce R star is the specific metabolic rate. Metabolic rate is just the amount of power, watts, that we produce, joules per second. Specific means we're going to do it per unit mass. So this is really watts per kilogram. So whenever we add specific in front of something, we're going to be talking per unit mass. So if we want to know, well, let's introduce one other variable. A is going to be some measure of a linear size. So I'll just call it the radius, but whatever it is, it's what scales us in a linear way. So how much heat is produced? Heat produced is going to be what? How much heat is an animal going to produce? And let's, how would we figure that out? Well, there's a specific metabolic rate. We want to know the metabolic rate for a given animal. Yeah, we're going to just take this R star, and we're going to multiply it by the mass. Now, almost all animals are made out of the same material, mostly water. So, really, if the density is the same in all animals, mass is going to be proportional to volume. So, really, the heat produced is going to depend on the volume, which is A cubed. Times there's some constant that has to do with the shape of the animal and maybe some other factors. But basically, this is a constant independent of size. This shows the heat produced depends on the volume. The more mass, the more volume you have, the more heat you produce. How do we get rid of heat? Well, we get rid of heat through our body's surface. So heat loss is going to be proportional to surface area. And surface area, if we're all the same shape but different sizes, is going to be proportional to this size squared, the radius squared if it was a sphere. And there's going to be some other constant that doesn't have to do anything with shape, but could have to do with, maybe if it was a sphere, it would be 4 pi. And if it was, it might have to do with how much hair you have, or other factors about how well heat couples it to the outside. But basically, heat loss goes as the surface. So, if you're in steady state, and we're all, at least over long term, in steady state, because we have a constant temperature, your heat produced has to equal the heat lost. So, if you're in steady state, you get R star, A cubed, a constant, equals A squared, B, and you divide through, and you get this prediction that A cubed over A squared gives you 1 over A times some constant, which I'll just call B over C. So what you get is that the specific metabolic rate goes to 1 over the radius. This says that large animals that have a big radius, like an elephant, you have a small metabolic rate. It's going to be very sluggish. Each cell in the body, because all cells are about the same, each cell in the body in a large animal is going to be working very slowly because it's a large animal. The problem is getting rid of the heat. It's got plenty of heat to keep it warm, and it's going to have a sluggish metabolism, otherwise it'll overheat. Where a small animal like a mouse, its big problem is losing heat. It's got so much surface area compared to volume that it has to protect from losing heat, and therefore it's got to have a very large specific metabolic rate in order to stay warm. So it's eating all the time, and cells are very active. So we've made a prediction about the relative metabolic rates of different animals just by looking at these general scaling arguments about heat loss and heat gain. And I'll go back now to Haldane, who we quoted from last class, and he has another quote in this on being the right size. And he says, comparative anatomy is largely the story of the struggle to increase surface in proportion to volume. So you see surface and volume coming in. Here is volume, here is surface area, and this ratio of surface to volume area actually plays a really important role in understanding how different animals compare. So we can go a little further. We can say that the mass, M, which is mass, it's proportional to, so we're going to be doing a lot of proportional twos in scaling. It's proportional to the volume. Everything's the same density, so A cubed. That means that A is proportional to mass to the 1/3. Because if you take the third root, you just get A, so you get mass to the 1/3. And that means R star is going to be proportional to, well, 1 over A mass to the minus 1/3. So it even gives us a prediction of how this sluggish specific metabolic rate changes with the mass of the body. Okay, now suppose you want to know the overall metabolic rate of some animal. Not how much per unit mass, but his total metabolic rate. Well, you just take the specific metabolic rate and you multiply by the mass. So R, without the star, which will be total metabolic rate in watts, is going to be R star times mass. That's just the definition, really. And so you got mass to the first power times mass to the minus 1/3. So how does R scale with mass? Anybody?
To the 2/3.
To the 2/3. 1 minus 1/3. The way that I'll put a proportionality sign. The way the exponents work is you get 1 minus 1/3. When you multiply them, you just subtract the exponents or mass to the 2/3. So you'd expect that the total metabolism, the total metabolic rate should go up as mass to the 2/3. Now, last class we talked about log plots and scaling and power laws, and this is a classic power law. If you plotted R and M on log paper, you'd expect to get a straight line with a slope of 2/3. So let us explore that a little more and see if we get that result. So, questions about this so far? Okay. Alrighty, so let me give you some data. I'll have an animal. I'll have its mass in kilograms. And I'll have its metabolic rate in watts. Okay, we'll start with a small mammal, like a mouse. What we're eventually going to create is what's called the mouse to elephant curve. The mouse has a mass of about 20 grams, or 0.02 kilograms. So nice little things. Its metabolic rate is 0.19. Okay, next up is going to be a guinea pig. A little bit larger, used a lot in scientific experiments. Its mass is about 0.5 kilogram. and 2.1 points of metabolic rate. Dog, everybody's favorite, is going to be about a 10 kilogram. Mine's a little more than that. She's a big fat thing. 19.7 watts. Then us, humans, and average is about 70, and its metabolic rate's about 85 watts. You used to be able to say that this was about the power production of a light bulb, but nowadays a light bulb is so efficient that it's maybe 4 of the more energy efficient light bulbs. And then we'll go on up to a really large animal, elephant, which has 3,000 and is about 1,400. Okay, so the total metabolic rate increases with mass, but even though it doesn't increase in proportion to mass, so the specific metabolic rate is still lower for the elephant. Now let me say a few things. First of all, this really works when you're comparing animals that are basically the same design. For instance, these are all mammals. If you start comparing mammals to, say, insects, it gets a little dicey because they're really designed differently. And second of all, it doesn't work too well if you only look over a very narrow range. For instance, if you're just comparing different humans who might have a mass of 70 versus 60 versus 80, other factors, random noise, things are going to cause a lot of variation. But when you start looking over large length scales, this tends to really gives you some good insights. So let us look now at the mouse to elephant curve. So I'll plot it here. And we're going to look on log paper. And remember, we wanted to have the same tick marks on each scale. So 0.01, we're plotting mass in kilograms. And that's going to be 0.1, and that's going to be 1, 10, 100, 1,000, 10,000. And we'll make our plots on this scale, which is going to be R in watts, and it's going to be 0.1, and then 1, 10, 100, 1,000, and I got to go a little farther, 10,000. Okay. Let's see if we can put this data on here. The mouse, 0.02. Remember, 0.02, that's between 0.01 and 0.1. It's about right here. And it goes up to 0.19. 0.19, so that's going to be about here. Is the mouse point. Next point is the guinea pig, a half. A half is going to be a little over halfway because of the logarithmic scale, about 2/3 of the way up. And 2.1, so about here. There's your guinea pig. Next up is the dog, 10. That one's easy. And goes over to 19.7. So we call it 20, which would be about right here. Dog. Human, 70. Not that far from the dog, really. And 85. Human. And now the really big one, the elephant, 3,000. So that's about halfway between 1,000 and 10,000. And it goes up to 1,400, so it's a little bit above 1,000 elephant. Now, if I drew these very carefully, these would fall on a nice straight line like this. And you can actually, since I was careful to make my tick marks in the y direction the same as the x direction, you can actually get out your ruler and you can measure the slope. And that would give you that exponent. Now, here's the interesting thing. If you do that, you will find that the slope, so if you represent this as r equals some constant, I'll call it c, but it's a different c than we had a minute ago, mass to the n, and we thought our model predicted n should be 2/3, but if you do the calculation, you analyze this data, n comes out to be 3/4. So at n to the 3/4 is a little bit of a mystery, and people are still trying to explain why you get 3/4 instead of 2/3. It's close enough that sort of the general ideas seem to apply, but it's not exactly what we'd expect. So that's kind of interesting, and there's a lot of analysis that's been done as to sort of why it might be 3/4 instead of 2/3. This is called Kleber's law. Kleber's law says that the metabolic rate goes as mass to the 3/4. So if we wanted to actually figure out what C is and try to get N more accurately, we could, instead of just measuring with a ruler, we could take 2 data points. So let's take the mouse is R is 0.19 equals C times M to the N, and mouse is 0.02 to the N, and we could take the largest ones. We could take 2 that are widely separated. 300, see R is 1400 equals C times 3000 to the N. Those 2 are enough. Now, what did we do last time? We wanted to try to get what N was? Divide the 2. If we divide the 2, the C's will cancel, and you'll get 1400 divided by 0.19, which comes out to be 7,368. And the C's cancel, and you get 3,000 over 0.02, which is a big number, 150,000 to the N. You can then take logs of both sides, or however you wanted to do it, you can get N. And N comes out to be 3/4, so 0.75. And then you could stick that into either of these equations. You calculate C. C comes out to be about 3.5. So you end up getting R is equal to 3.5 M to the 0.75 is your scaling law for metabolic rate. And with these scaling laws, you have to be careful to specify the units, because really this number here has really strange units because it has its M to the, so it's going to have 1 over kilograms to the 3/4. It's got to give you watts. So you should specify that this is in watts and mass is in kilogram. You'll get a different type of a law if you have different units. All right, so I want to just talk a little bit more about this just to show you how interesting these scaling laws can be. Let's look at the smallest mammal. The smallest mammal is not a mouse. Anybody have an idea what the smallest mammal is? Yeah.
Isn't it a bat?
No, bats can be they're small, especially if you realize that almost all their mass is in their body when their wings don't give one. But there's an animal called a shrew. I can't really fit it here. I'll try to fit it here. It's gonna have to squeeze it in. A shrew is a tiny little mammal. It's got a mass of 3 grams. A gram is kind of like a paper clip. So this is a really small mammal. And it has to have a metabolic rate is 0.045. So you might say it's small, but if you calculate what the specific metabolic rate is, it's up around 15 watts per kilogram, which is really big. The shrew has to just eat all the time. Otherwise, it's such large surface area compared to volume, it would just freeze and not freeze, but it would go to the temperature of the surroundings and its metabolism wouldn't be warm-blooded. The same thing happens with birds, these tiny little hummingbirds. They're real small. They just got to eat all the time. Because the cells, think of individual cells in the shrew or the hummingbird. Those cells are really chugging along, doing a huge amount of metabolism. The largest mammal, you might think, is the elephant. We're not going to do dinosaurs because they're reptiles. But the largest mammal is actually an extinct mammal. It's this thing that's called, I'm going to put my glasses for this one, a Baluchitherium. It's like a big rhinoceros. I believe it was native down in South America. And it's got a 20,000 kilogram mass. So it's almost 7 times an elephant. Its metabolic rate is 5900. Its specific metabolic rate per unit mass is about 0.29. It's really slow. These really large animals, their main problem isn't staying warm. Their main problem is staying cool. So, and that's why a lot of the big dinosaurs, which are reptiles, which are not warm-blooded, and you might wonder, how do those reptiles, no hair, how do they stay warm? And but that's not their problem. They're so big, their problem is to stay cool. And that's why things like elephants develop these big ears. A lot of people think that those ears are mainly heat sinks to get rid of excess heat because large animals, heat loss is really important. So you can kind of see a wide range of comparative anatomy and comparative physiology for these animals. If you like this kind of thing, I'll recommend another book, Scaling: Why Animal Size is So Important by Knut Schmidt-Nielsen. Has a whole lot of analysis similar to this, plus other ones. Some of your homework problems are drawn from topics in this book. So if you like animal scaling, there's several good books. This one's my favorite. Alrighty. Now, questions about heat loss? Yes?
Do the numbers there vary with climate?
Yeah, things would vary with climate. For instance, rabbits. The rabbits that live around us have some fur. Rabbits that live up in the Arctic have a whole lot of fur. So there's going to be differences in climate. I think differences in climate would be important when comparing over small mass ranges. When you're comparing over these really large mass ranges, those issues, I think, are going to be swamped by these general scaling arguments. If anybody wants to know why it's n to the 3/4 instead of n to the 2/3, there's some references in the book. Basically, people have made arguments based on the way our blood vessel system sort of branches in a fractal way and come up with explanations why it might be n to the 3/4. It's a very subtle question, but it's kind of a fundamental question in biology because you really want to understand why you have a fairly good, at least over all mammals, this n to the 3/4 scaling law. So it's really a fascinating issue. Okay, I'm going to erase this, and we're going to look at another example. This example goes all the way back to Galileo. Also, if you look at the Haldane book, this is the very first example he does in his essay on being the right size. We're going to look at how size of bones depend on body size. So, as usual, we're going to compare basically how much weight the bone will have to support versus how strong the bone is. So the weight of an animal is going to be proportional to its mass, mg. And that means proportional to its volume. So it's going to be volume. And that means that the length of a bone, if bones were going to scale up in proportion, if all animals were the same shape but just different sizes, the length of the bone would scale up the cube of that as the mass, so that the length of the bone would go as mass to the 1/3. However, how strong does the bone have to be? Well, that bone has to support this whole weight. You can get bones stronger in two ways. You can make them out of different materials, but it turns out most animals have their bones made out of the same material, like calcium, and there's not that many ways you can improve the material of your bone. And you can also make your bones thicker. So if you make your bones thicker, the bone strength is going to go as the area. And the area, if you're just scaling up the bone, is going to go as the size squared. It's kind of like a surface area. So that means that the radius of the bone, you expect it, well, the area is the radius squared. So you set the radius of the bone squared proportional to the mass, because it's got to support that weight, so it needs a larger cross-sectional area. So now let's look at the aspect ratio. Aspect ratio is just the ratio of the radius to its length. Dimensionless number telling you how thick bones are compared to their length. And that's going to be, this should be proportional. The radius is going to go as the mass to the 1/2, because if I take the square root of this, I get the square root of that. And the length is going to go as mass to the 1/3. Mass to the 1/2 over mass to the 1/3. What's that come out as?
1/6.
1/6. That's mass to the 1/2 minus 1/3, because it's downstairs. 1/2 minus 1/3 is mass to the 1/6. So this says that bones for bigger animals ought to have a bigger aspect ratio. In other words, bones in large animals ought to be thicker compared to small animals. And you can kind of see this. And the example I like is the daddy long-legged spider has these really, really thin little legs. And how can those little legs support that mass? Well, it's because for an animal that small, you don't have much weight compared. You don't need much cross-sectional area to compare that to support that very small weight. So for a small mass, you have an aspect ratio that's very small radius compared to length. But if you get to larger animals, it's more of an issue. So here's a picture. Okay, so now this is a picture of a human femur. So, of course, I scaled it down, but let's imagine you took a photograph of the human femur. Then you took that photograph and you just, in your computer, scaled it up by a factor of 3. So magnified it. What you get is this, human femur scaled up by a factor of 3. All right? Now you compare that to an elephant. Well, an elephant is going to actually have a bone, a femur, that's about 3 times as long as a human. But it's not just a scaled up version. If you look at the elephant's bone, it's much thicker than you'd expect for a human, because it has to support that much more mass. So that's really what we mean by the aspect ratio. Increases with mass. Anytime you have a positive exponent, increases. Not real fast with mass, but it does increase with mass. To give you some numbers to kind of put on this, let's compare the mass of a human, which we said was about 70 kilograms, and the mass of the elephant. Okay. In the previous example, I used 3,000, but I want the numbers to come out right, very nice. So I'm going to use a sort of a smallish elephant, or maybe it's like a big cow or something, a buffalo. I'm going to call it 1890 of all things, kilograms. I can compare what aspect ratio you'd expect. Now, why would I take 1890? Well, if you take 1890 and you divide by 70, you find that this mass is 27 times the human mass. So 27 times a change in mass. Well, that means the length of the bone, if the mass is 27 times, we said the length of the bone goes up, it's the cube of the mass. So the length of the bone should go as mass to the 1/3. What's the third root of 27? 3. 3 times 3 is 9, times 3 is 27. So the length should go up by a factor of 3. That's like I showed in that picture. But the radius is also going to go up, but the radius goes up as the square root. Okay, this is a little harder. Anybody know the square root of 27?
5.
It's a little over 5. Square root of 25 would be 5. This comes out to be about 5.2. So the aspect ratio then would be 5.2 over 3, which would come out to be about 1.73. And that's really close. I mean, I designed this picture to have that kind of aspect ratio. So, small animals can get away with really small, thin bones. Big animals have to have these great big bones. Another example of scaling at work. Alrighty. Let me talk a little bit about some of the homework problems before we go on. Any questions, though, first about animal bones? A friend of mine who's at the University of Oregon is lucky he has a elephant skeleton at his university, and he's able to bring the bones actually into class and show the students their different shapes. And I wish I had that to show you, but I don't. Okay, the last 4 problems. First of all, 2.42 in your homework. This problem is designed to compare 180 people, each with 70 kilograms, to 12,600 chickens, each with 1 kilogram. And you're supposed to compare 2 things. Compare their mass, and you're going to find out, just kind of give it away to you, you're going to find out that these numbers of chickens was picked so that they just match exactly the mass of the 180 humans. And then you have to calculate their metabolic rate. And remember, chickens are a smaller animal, so they're going to have a higher specific metabolic rate. So each cell in their body is going to be more active. And what you're going to find is those chickens, even though they have the same mass as the humans, create a huge amount, much more metabolic metabolism, a lot more food needs, a lot more metabolism, a lot more waste products, carbon dioxide given off. There was one time when some people wanted to transport some chickens, and they were desperate to get the chickens across the country, so they got an airplane, like a 747 or something. And an airplane usually handled 180 people, so they stuck in the 12,600 chickens, figuring, same mass, they have the same weight, they ought to work. And the airplane got foggy, and it just it was a disaster, because all those chickens producing all that heat really caused some problems. So that's homework 42. You can do that quantitatively. All right. Homework problem, next one, 46. Homework problem 46. I better read it and see what it is I gave you here. Chapter 2, number 46. In problem 45, well, you didn't have to work 45, but that was basically the mouse to elephant curve we did in class, essentially problem 45. So in problem 45, you found how the specific metabolic rate varies with mass. If all animal heart volumes and blood volumes are proportional to mass, then the only way for the heart to increase oxygen delivery to the body is increasing the frequency of the heart rate. So, now you've got another issue. Again, you could design just more better hearts, better blood, but animals don't do that. Animals are all made out of basically the same hearts. So the only way you can really keep the specific metabolic rate high in small animals is to have a really rapid heart rate. So what you're going to do is you're going to calculate basically what the heart rate is for different animals. Have to work out the scaling law and calculate it. Another homework assignment. I want you to go take your little pet gerbil, and I want you to take its pulse. Then I want you to go to the zoo and climb over the fence and go take the pulse of the elephant. And what you're going to find is the gerbil's little heart is going beep, 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 and the elephant's heart is going beep, 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 beep. Because it hardly has to pump any blood because its specific metabolic rate's so low. Don't actually climb over the fence into the elephant. But the idea is it's interesting to look at the heart rates. And if you just want to do a simple case, take your nice little Cocker Spaniel and take its pulse, and I bet you'll find its pulse is higher than yours if you're both sort of in a resting state. So we're going to look at the heart rate. And then you're going to look at, in problem 47, I want you to look at the height that people can jump or animals can jump. So we're going to start, and it goes through and kind of gives you the way to derive the scaling law. So your goal is to figure out some scaling law. The height that an animal can jump is equal to some constant times mass to the n, and you got to figure out what n is. And I'll tell you the answer because it's given in the very next problem, 2.48. The first line of 2.48 is, you should have found in problem 2.47 that the height you jump is independent of the mass. So the bottom line is n equals 0 is an okay result for scaling law. But, so that means that even small animals like a flea jumps to about the same height as we do. It's not exactly the same, but fleas can jump up, pretty high, and so can humans about the same height, even though they're drastically different masses. So n is 0. But there are differences between humans and fleas, and it becomes clear when you start looking at accelerations. What this problem 2.48 asks you to do is basically see how long it takes to jump and to get up to speed and figure out the acceleration that a human undergoes when they're jumping straight up. And then figure out the acceleration the flea undergoes when it's accelerating. And what you're going to find is that the acceleration does scale with mass. And the conclusion is that I come away from that problem not understanding why fleas don't have concussions every time they jump. Because they have huge accelerations that if we experience those accelerations, our brains would get slammed against our skulls and we would either die or have serious brain damage. Somehow fleas avoid that, and I'm not quite sure how they do it, but it'd be an interesting thing to study if you're interested in comparative anatomy. So the bottom line is these last 4 problems in your homework assignment are all about animal scaling, all kind of doing the same thing. And that, we discussed the other problems earlier, so that is the homework for Chapter 2. And I would suggest you get to work on it, so on Wednesday you can bring in your questions and we can ask questions about it so that you can get your questions answered before it's due on Friday. Any questions now? Anybody who got a real early start that has questions on homework number 2? Yeah, I always encourage you to get early start, but I realize you guys have a lot of things on your plate. Okay, I want to do one last example, not in your homework, for scaling law. So I need some help on this one. All right. We're going to look at walking speed. How fast can different animals... Yes.
I'm sorry. For some help, do you mean like a volunteer?
Yeah. I'm going to be calling on you guys to asking you questions. Yeah. So, I want to look at walking speed. So how fast can various animals walk? Compare me to the elephant to the mouse. Who's going to win the race? Basically is what we're going to want to know. So, first thing we have to do is we have to ask ourselves what's involved. There is how far each step goes, and there's how fast each step goes. So, let's first do the length of a step. How do you think the length of a step would scale with mass? So this is where I need you guys' help. Who's got an idea? Yeah.
I think the length of this step would probably increase with mass because the length of your legs would also probably, or the length of the legs bones would probably increase with your mass.
Absolutely. But let's see if we can be a little more specific. Let's see if we can say that the length of a step per step is going to be proportional to mass, and you basically convinced me it's going to be a positive exponent. It's going to go up with mass, so there's going to be an n here. And now the question is, can we do even better? Can we say what that n, which I'm going to erase with the proper number here in a second, is going to be? Anybody have an idea for that? Yeah?
So we just just said the length of a bone scales at a good rate with mass.
Mm-hmm.
So, I think a leg is going to be about 2 bones in length. Would it be m to the 2/3?
M to the 2/3? What did we say that the length of the bone scaled as?
Length of bone cubed relates to mass.
Cubed. So then how would the mass relate to the if mass is proportional to L cubed? What's L proportional to?
Mass would be 1/3.
1/3. Yeah. So mass would go up as 1/3. So what we're saying is that if all animals are made the same shape but just different sizes, the length of that step should go as mass to the 1/3. So the bigger linear scale, the larger the step length. So I've got a big advantage over the little mouse because my stride is vastly bigger than the little mouse's stride. So the mouse is going to try to make up for it with a faster little speed. So let's see now. We need to look at the time per step. And here is where it gets a little tricky. Because when you're walking as opposed to running, your leg is basically a pendulum. Your leg swings, and the natural rate of walking is the natural rate of swinging of the pendulum of the leg. So does anybody remember how the period of pendulum varies with the pendulum size?
With length.
Pardon?
With length.
With length. How does it vary with length?
1 over.
Okay, this goes all the way back to Galileo, who, when he was in the church and he needed a clock, he used the pendulum of the candelabra or whatever it was hanging down from the ceiling of the church. we gotta try to remember how that period goes with length. Anybody want to?
Isn't it directly proportional?
It's not directly proportional. That's why it's a little tricky. If you go back and you remember your oscillatory motion from Physics 1, you'd find that the period goes as the square root of L divided by G, which is the same for everybody. But L over G is the how the frequency of a pendulum varies with its length. So if the time step goes as L over G, that's the time per step, which is the period. So that means that small animals have small time per step. So small animals are really going like this, and big animals like me are kind of going and walking along with much slower time. But how did L depend on mass? You just said that. Mass to the 1/3. So how does time step depend on mass?
The 1/6.
The 1/6. Square root of 1/3, that's kind of like saying mass to the 1/2, I'll put 1/3, that's L, is mass to the 1/3, raised to the 1/2 power, which is square root. And when you have 1/3, m to the 1/3, all to the 1/2, that's like multiplying the two, mass to the 1/6. So, the time per step, or the period, goes up with mass also, but not quite as fast. So now, how about the speed? How do you think the speed of walking varies? What could we do to figure out the speed of walking?
Length over time.
Length over time. And so let's, particularly for one step, you should have a length per step over time. Per step. So this per steps cancel, and you just get length over time, and this is going to be proportional to m to the 1/3 divided by m to the 1/6. And it's similar to what we did before. 1/3 minus 1/6. So that's going to be mass to the 1/6. So, big animals, since this is positive, big animals have faster. So if you're trying to race an elephant, you're probably going to lose that race. If you're both walking and probably running too, you'd lose the race. And it's not because, it's because the elephant has longer legs and it's just going to have a longer stride. And even though you're going to be able to go faster than the elephant, it's not going to make up for the longer stride. So the elephant's going to be a walk along. It's going to look like it's kind of lumbering along, but its actual speed is going to be faster than yours and a lot faster than mouse. So I don't know why elephants are afraid of mice, or so they say, because the elephant ought to just be able to walk away from the mouse and the mouse will never catch up. Yes?
Well, I saw a video once that, sort of exaggerated in cartoons, but really they just sort of momentary back away in surprise.
Well, it's true that, you start, if you really got into details, you'd have to start talking about accelerations and things, and certainly once you got up to speed, the elephant could walk away. Whether the elephant could actually escape over the short term when you're dealing with accelerations is another story. But yeah, that shows you how animal scaling goes, speed goes with mass. So here's a question. Suppose now that this is similar to the kind of things you might have on an exam. You know that speed goes as mass to the 1/6. You have a human, which is a 70 kilogram mass, walks about 5 kilometers per hour. How fast does an elephant, which is 3,000 kilograms, a big full-size elephant, how fast does it move? How are you going to solve that? So it walks how fast? All right, so we know that the speed, I'll call S the speed, is going to be equal to some constant mass to the 1/6. We figured that out. We haven't figured out what the constant is. There's two ways you could do it. You have enough data here with the human, the mass, and its speed. You can just calculate C. Easier way is to make a ratio. Is the speed of the human is equal to C mass of the human to the 1/6, and the speed of the elephant is equal to C mass of the elephant to the 1/6, and divide. So what you find is that the speed of the human over the speed of the elephant is equal to, the C's go away, mass of the human over mass of the elephant, the whole thing to the 1/6. So if you want to know how fast the elephant goes, you can solve for S elephant, and it's going to equal S human. And when you bring this to the other side, the mass of the elephant comes up here, mass of the human goes down here, the 1/6. And you're going 5. Nice thing about doing this is you don't have to worry now about units, because S will always be in the same units, M is the same units, C had funny units, but it canceled out. So the human walked 5 kilometers per hour. Mass of the elephant was 3,000. Mass of the human was 70, the 1/6. You can immediately solve it. And 3,000 divided by 70 means that the elephant is 42.8 times as massive, but if I raise that to the 1/6 power, it means it's only 1.87 times as fast. Because basically, speed increases with mass, but pretty slowly. Times 5, which is what the human does, and the elephant goes at about 9.4 kilometers per hour. So it's so weak of a exponent, so small of an exponent, that the change in speed isn't real dramatic with mass, because we're much more massive, only slightly faster for the elephant. All right, and if you measure how fast elephants go, they're actually a little bit slower than this, but not much, around 7.5 kilometers per hour. Sometimes these don't get it exactly right. These are general scaling laws. They assume all animals are sort of made the same. We're clearly not made the same as the elephant, because we walk on 2 legs and the elephant walks on 4, plus other differences. But it is sort of impressive that it gets it pretty close. All right. That is what I wanted to cover today. So we're done a little bit early, but let's just remember next class we're going to start Chapter 3. Chapter 3 has a lot of really fascinating information about thermodynamics at the start, and developing thermodynamics from a statistical point of view, we just don't have enough time to do it. So I apologize for having to skip that, but you're going to start in section 7 through 10 is what we'll be talking about. We will never be covering the first part of the first 6 sections of Chapter 3. We'll be talking about thermodynamics, and you have an exam Monday, September 30th, and it will cover chapters 1 through 3. So we've done chapters 1 and 2. We'll go on to chapter 3 then. I handed out back the homework before class, but if you came in late, you can come get it from me now. Any last questions? All right, then I will see you on Wednesday.